Hello, and welcome to today's webinar. My name is Bruce Korn, and I lead Geosoft's business in the energy industry, and I'll be hosting today. We're glad you've joined us for today's webinar on VALEM for GM-SYS 3D, improving exploration effectiveness in the subsalt with hybrid gravity inversion. So today we will be looking at and demonstrating VALEM, which is voxel-assisted layered earth modeling, a hybrid gravity inversion within GM-SYS 3D, which is our 3D gravity modeling solution. At Geosoft, we believe that 3D earth modeling is best when it involves iterative collaboration between the geosciences. To improve subsalt imaging in the energy industry, we've developed a hybrid modeling method that augments seismic modeling with potential field data. We also believe that 3D modeling should be fast and intuitive, so we've combined the speed of high-performance computing in the cloud with the 3D model building environment our users rave about, which is GM-SYS 3D. Joining me today is Gaude Pouloucan, who is our presenter. She is a technical analyst at Geosoft with potential field experience in the oil and gas industry. She will discuss and demonstrate Geosoft GM-SYS 3D and VALEM on a synthetic data set. She will close with some real-world results from offshore West Africa. Taronesh Pithiwala will follow Gaude to answer your questions during the Q&A session. He's a geophysical modeling specialist who focuses his time on inversion modeling. Thanks again for joining us today, and I will now hand it over to Gaude.
Thank you, Bruce, and thank you to everyone for joining us on online today. So in today's webinar, we looked at our recent work on inversion and how we can enhance seismic imaging of the base of soil using gravity. So as you all know, subsalt is a challenging environment, so I'll briefly introduce the challenges we're facing, both from a petroleum perspective and a potential field modeling perspective. We'll look then at how hybrid modeling and our new application VALEM can address those challenges. Then I'll show you how to complete a bed of salt inversion step-by-step in OASIS montage using GM-SYS 3D and VALEM. For this, we'll be using a synthetic salt model developed by the SEG. And as Bruce said, to finish, I'll show you some preliminary results with real-world data in offshore Africa. And finally, we'll wrap up the webinar with a question and answer session with myself and Taronesh. So, why do we need gravity for subsalt exploration? Well, seismic data usually does a good job of defining the top of salt, as you can see in the example here. And it often images the base of salt where the salt body is thin and tabular. However, it has difficulty imaging the base of salt where the salt boundaries are not relatively flat, like it is here. Where there is sufficient density contrast between the salt and underlying sediments, gravity can play an important role in defining that interface. In today's webinar, we'll look at how we can reduce uncertainty on the geometry of the base of soil using gravity data. So how can we achieve this? Well, we can try to increase confidence in the seismic model. And in subsalt regions of complex lateral velocity variation, seismic imaging usually involves a pre-stack depth migration, or PSDM. PSDM is a model-driven technique. It requires to construct a robust velocity model. So what we need to do is find a way to add some constraint to our model by integrating gravity within the workflow. And what we did with VALEM is that we designed and implemented a modeling strategy that can use gravity to constrain the base of salt and be an integral part of the PSDM modeling cycle. So we talked about seismic, but salt is also challenging for gravity modeling. But the traditional approach to gravity modeling is layered earth modeling, where the main interfaces, or density domain, are defined by layers, like you can see on the top right here. Between these layers, density are defined by constant, single value grids, or depth density function. So it can work to invert the base of salt. However, it has its limitation. models are complex to build and usually require intensive manual intervention. For example, handling 3D density distribution is not straightforward. And it means that a 3D density distribution is often approximated by vertical density depth function, as you can see in this example on the bottom right of the screen. So the consequence is that it makes seamless integration with the velocity building process often more difficult. However, it also has some strength. Calculations are done in frequency domain, so it's a fast process. So how can we build a more efficient and optimized modeling strategy? Well, we can introduce voxel-based modeling. But voxel inversion also has challenges to overcome. So let's start looking at the pluses. Well, first of all, it is more flexible. We can assimilate complex geometry and 3D density distribution into the model, like you can see here. And this is highly appropriate for subsalt problem. There are, however, some downsides. It is much slower than the layered earth approach and subsequently requires more computational power. Another issue is that when left unconstrained, potential field inversion produce non-unique interpretation. Also, voxel-based inversion tend to produce smooth transition between domains when what we're aiming at with the base of salt is to recover a sharp salt sediment interface. So really what we need to do is to take the best of both worlds and put together layered earth modeling and voxel-based inversion. And that's why we introduced VALEM, which combines the two using a hybrid modeling approach. So as Bruce already said, VALEM stands for voxel-assisted layered earth modeling. So I want to point out now that VALEM is tightly integrated in Geosoft layered earth modeler, GM-SYS 3D, and available only within GM-SYS 3D. It means that the starting model for VALEM inversion is built within GM-SYS 3D. So VALEM models are flexible and allow the use of 3 different types of data structures, layers, voxel, and 3D triangulated surfaces within a single model. Modelers can use the most appropriate representation for each model element and quickly build complicated models. So the model can include a starting 3D geosurface interpreted by the seismic modeling team, can include various relief layers that will define known constraining layers in the model, a full density voxel model, again usually derived from the seismic or directly given to you by the seismic team, and a detailed bathymetry grid that accurately defines the water seafloor interface. And it can also introduce advanced constraint functionality which are highly appropriate to the subsalt problem. So to summarize the benefits of VALEM hybrid approach, first of all, and importantly, it can handle complex 3D distribution and can limit non-uniqueness by allowing the user a wide range of constraints. So I'll talk about this and the importance of a robust starting model in more detail during the live demo. It's fast. So how do we make it fast? Well, it gives you high performance computing power that scales right on your PC desktop. As I said, it's tightly integrated with Geosoft GM-SYS 3D modeling program. So what VALEM does is that it leverages the workflows within GM-SYS to simplify and speed up the inversion modeling process. And although VALEM inverts a density voxel, it returns a layer to the GM-SYS 3D model. So what it does really is that it makes building models and collaborating with the seismic team easier. So I mentioned earlier that potential field inversion are inherently non-unique, which means that a multitude of models can produce the same gravity anomaly. So how can we reduce non-uniqueness? Well, VALEM's hybrid approach provides greater potential to address the challenge of non-uniqueness. That's because we can introduce constraints to the model based on what we know from the geological and geophysical interpretation. You can, for example, include faults, well logs, varying uncertainty into your starting model. So I also mentioned earlier that voxel-based inversion tends to return smooth transition between domains. And in the context of salt, what we want is to recover a sharp interface between two domains, the salt and the sediments. So what we did to overcome this is that we implemented the iterative reweighting inversion, or IRI, methods, which effectively produces either a target domain, or salt, or a host domain, the sediment, with a sharp transition. So IRI takes an initial inversion result and uses it as an iterative reweighting constraint in the subsequent inversion. This process is repeated several times in order to produce a refined or focused final inversion result. So to show you an example, in the image on the right here, okay, you see the salt body in blue. And you can see an example where the salt sediment boundary is much sharper using IRI. So if what you're seeing now is the result with IRI, and I'm going to flick a few times, okay, and show you the result without IRI. You can see a far smoother transition here between the blue and the light blue and green toward the sediment. So going back, yeah, sharp transition with IRI, without IRI. So how does a base of salt inversion works in VALEM and GM-SYS 3D in practice? Well, base of salt modeling is very much an iterative process, and VALEM functions as an integral part of the interpretation cycle. So it starts here at the top with the seismic interpreters producing an initial velocity model. This model is then converted into a density distribution cube. So in the real world, this would usually be done by the seismic team itself and not the potential field team. This density cube might or might not already contain a preliminary salt model. So in this example it does. So if it does, we next remove in the next step, we next remove the salt from the model to build a starting or what we call a reference model here. Then the various components of the model are integrated into GM-SYS 3D, or layered earth model. And doing so, we can easily separate what is known from what is unknown. And we turn to the VALEM inversion to solve for the unknown, which should be everything remaining related to the salt. Okay, so that's that residualized model here, and the real residualized gravity anomaly. We send that to VALEM, and at the end of the cycle, we get a base of salt horizon, okay, which is here on the top left, which can be fed back to the seismic model for validation and or for another iteration to refine the model further. Okay, I'm now going to move to the live demonstration and show you how we work that cycle in practice. Okay, so in the live demonstration, as I said, we're going to look at how to complete this inversion cycle step by step. So the model I'll use to demonstrate VALEM today is a version of the 1996 SCG research model. This model was designed to generate 3D marine acquisition and test PSDM algorithm. So it's based on a typical US Gulf Coast salt structure, and on this map here you can see the seafloor in blue as a relief surface and the salt body as a triangulated surface. I can also choose to represent the top salt and base salt relief surface with colored elevation. At the top, I can overlay the gravity response of the model. So this salt model has challenges for gravity modeling, such as thinning edges and a deepening extension toward the west here. So here we are at the start of inversion cycle, and in the background I'm now going to display a voxel representation of our initial velocity model, which was generated by the seismic team. Okay. I'm now going to turn off the velocity and display the density distribution through the model. In this example, the density voxel was calculated by converting the seismic velocity cube. So this can easily be done within OASIS Montage by using one of the pre-built functions existing in GM-SYS 3D toolbox, or simply by using the voxel math tool to apply an empirical velocity density relationship, for example built from well logs in the vicinity of your area of interest. However, as I said earlier in my presentation, in most cases I would expect the density cube to be provided to you by the seismic interpretation team. Okay, if I scroll through the model, you can see that my initial density model includes a preliminary interpretation of the salt. So in today's scenario, we want to test VALEM ability to recover a base of salt without any prior information on the salt thickness. So in the next step, I remove the salt from the density cube and flood it with a laterally interpolated conformable sediment film. Okay, I'm now going to display this reference of our background model on the screen. Okay. Okay, and you can see that we don't have any salt left in the model. No, VALEM is tightly integrated within the GM-SYS 3D, the layered earth modeler. And now that we have a density model and a top of salt horizon, we can start building the model in GM-SYS 3D. So we use relief surfaces to define our main boundaries, and the reference density voxel that we've just built to assign physical property to each layer. So I should remind you here that in GM-SYS 3D, layers and body can be defined using elevation grid and triangulated surface. Within these layers, densities can be defined either with constant value, density depth stable, can be laterally variable, or defined with a voxel. And you can add gravity and magnetic surveys for forward and inverse calculation for either structure or physical properties. Okay, so now let's go back to our SEG salt model. Here I start building the model with a top layer or sea surface, which has a constant elevation of 0 meters and a density, selected, a density of 1.03 gram per cubic centimeters. Below it, the seafloor is defined by bathymetry grid, and the density beneath this layer, beneath the seafloor, is defined by the reference density model. So defined with a voxel, as you can see here. I can now add my top salt. Okay. I'm confident on the seismic interpretation of the top of salt. So when I run my VALEM inversion later, I will constrain the salt to stay within the polygon delineating the true top of salt. Now, if you're not a GM-SYS user, I'd like to emphasize here that in GM-SYS, I calculate the response of a layer-based model using fast Fourier transform. So when added layer, they must be continued to the edge of the model. Therefore, have expanded the top of salt elevation grid. And to show you this, I'm going to go back to my first voxel representation. Sorry about that. Wrong map. And you can see here the outline of the top of the salt surface in black superimposed on the expanded grid that we are using in GM-SYS. So I'll go back to the model. So for the salt body itself, I have specified a density of 2.2 grams per cubic centimeter in my GM-SYS model. As I mentioned earlier, in the first pass of determining the base of salt, I begin with 0 salt in the starting model. And I can simulate this very simply by defining my base of salt layers with the same relief surface as my top of salt. Okay, so I'm now going to switch on my starting base of salt. Okay. Remove the bathymetry to make it easier to see. Okay, and you can see that my top, despite different color scale, my top and base salt are identical in this starting model. So below the base of salt, to the bottom of the model at 5,200 meters below sea level, the density is defined using the reference density voxel again, as you can see here. So you can check the density distribution within the entire model, either simply by exporting the density voxel for the whole of the model, or along a particular section extracted from your GM-SYS model. Okay. And here is a cross-section going through the apex of the salt model, and it shows you the density distribution. So the white dashed line represents the true top of salt, which, as you can see, has been extended here to the limit of the model. And you can also notice the smooth density distribution of our reference sediment model. Okay, so I've built my starting model. I can now calculate the gravity response of the starting model, okay, and display the observed calculated and the difference or misfit between these two grids. So let's have a look at the misfit grid. Okay. So here the white polygon outlines the limit of the top salt, of the true top salt. Okay, the yellow line shows you the location of the profile I've just shown you previously. And you can see that the misfit is largely concentrated in the area within the top of salt, in particular here around the apex. And this is because we took caution to ensure that our model was as accurate as possible outside the salt. In order to effectively recover the base of salt from the VALEM inversion, it is really important to minimize the misfit elsewhere in the model outside the salt. Or in other words, to build a well-constrained, geologically realistic reference model. The more you know outside the salt, the more confidence you'll gain on your recovered base of salt. So I can go back to my section, and have a close-up view of the model. Okay, we can look at the misfit along that section, going through the apex, and you can here note the maximum misfit of about 2 milligal between the observed and my starting model here. So once I'm satisfied with the misfit in the remainder of my model, I can proceed to perform a VALEM inversion on the base of salt layer. Okay, so go back to GM-SYS 3D. So as I say again, VALEM is tightly integrated within GM-SYS 3D. The computation is performed through high-performance computing using the VALEM cloud service. And at the end of the inversion, a base of salt layer is returned to GM-SYS 3D and is assimilated into the model. Okay, so I'm going to start an inversion. So I'll start by giving my VALEM inversion a unique descriptor. Since I'm confident in my top salt relief surface and the extent of my polygon, I can limit my VALEM inversion to only my area of interest, and I do this by bringing a predefined polygon. Okay, I can constrain the horizontal extent of my base of salt with my area of interest polygon by checking this box here. And it ensures that the salt doesn't bleed into unwanted parts of the model during the inversion. So in my PowerPoint, I introduced IRI focusing earlier that we use to sharpen the salt sediment boundary. VALEM has also been optimized by default to return sharp layer boundaries by using an IRI focus factor of 3, as you can see here. Once I click Create, VALEM optimized the model for base of salt inversion by creating a series of constraints. The proprietary VALEM inversion package, okay, I'm just going to have done it ahead of time, so I'm going to stop now to save us a bit of time. So the package is then sent securely to the Microsoft Azure High Performance Computing Service in the cloud. Once the inversion is uploaded, you are free to work on other projects. You can close Oasis Montage, or you can even shut down your computer. Sorry about that. I realize I think you had lost my screen for a few seconds. So once the inversion is completed, the alternate relief surface is timestamped, as you can see here, and added to your GM-SYS 3D model for viewing. So you can then compare the starting model layer, okay, which is shown here, to the recovered layer by simply switching between them in GM-SYS 3D. Okay, so let's do this. Here was the base of salt prior to inversion. Okay, I remind you again that it was equal to the top of salt and therefore represented 0 salt thickness. Okay, and here is the base of salt after inversion. Okay, so I'm switching between before inversion and after inversion, and you can see that VALEM has added salt to the model. So to validate that the inversion results improve my overall model, I can make the active, that inverted base of salt the active relief surface and perform a forward calculation to observe the change in my misfit. Okay. So we can compare the misfit grid both before and after the VALEM inversion. So both grids that you're going to see have been colored using the same linear scale. So before the VALEM inversion, that's what you see here. When there was no salt in the starting model, the misfit was small, about 2 milligauss, and localized here within the region of the salt body. After the inversion, you can see that the misfit has been drastically reduced and shows that VALEM was able to recover a model that satisfied the observed gravity data. So I can also export and display the GM-SYS 3D model as a cross-section across the salt body. Okay, I'm going to use again the same section than before, highlighted with the yellow line here on the map. So in this section, the top of salt and recovered base of salt are shown in black, and the true base of salt is shown with a dashed white line. So in this view, you can see where the top and bottom of the salt boundaries were extended to fit the 3D model on the left here and on the right. And again, I reiterate here that both boundaries are extended such that the salt is limited in lateral extent, and limiting the inversion to the area of interest polygon ensure that salt does not bleed into unwanted parts of the model. So the observed and calculated gravity response is shown above. Okay, calculated in grid, observed in red. And you can see that the inversion did a good job and was deemed successful after we achieved the optimum data fit here. So we can also view the result in 3D to better appreciate the VALEM inversion. Result. So the VALEM recovered salt is shown in green, and the true salt body is in pink on the screen. So the VALEM recovered base of salt is close to the true bed of salt. You can see that the inversion was able to successfully model a dip in extension here, as well as the thin edge of the salt body. So in some regions, salt thickness was overestimated or underestimated. And this is of course a reminder of the non-uniqueness of potential field inversion and the fact that our input parameters and the constraints we put in do have an impact on the end result. So we can explore the results a little bit further by looking at the density misfits between the true model and our recovered density model. So what I've done here is that I've clipped the density voxel so that we look at a central section crossing the salt body. And to locate you, I can put briefly the observed gravity here. And here is the true top of salt surface. Okay, switch them off. So outside the limit of the salt, the densities are unchanged, of course. Within our active area of inversion, below the top salt, highlighted in gray here, the salt and sediments density are perfectly recovered. So the yellow here is going toward 0. So remaining discrepancies here and here highlights areas where we've under or overestimated the salt thickness, the same areas I was showing in the 3D map. So as we saw in the section map, the inversion was able to recover the salt body really well. Recall that in this example, we wanted to demonstrate VALEM ability to recover salt thickness without any prior information, apart from the top of salt. We started with no salt thickness. At the first pass, the VALEM inversion was able to give a reasonable estimate of thickness, lateral extent, dip of the salt body. So this will be a useful guide for the seismic depth migration later in the cycle. So today we looked at one scenario where we use VALEM to produce a base of salt to constrain the initial velocity model. But many scenarios are possible, and VALEM and GM-SYS 3D can also be used to fine-tune or validate existing salt model or test geological concepts from the seismic processing in conjunction with gravity field observation. And to make this easier, if I go back to GM-SYS 3D, In GM-SYS 3D, you can now also integrate complex body to your model. Represented by a triangulated closed surface, such as GoCAD T-Surf, for example. Okay. And in Oasis montage, we call these surfaces geosurfaces. So this can be useful, as I said, to validate geological interpretation quickly in GM-SYS 3D in conjunction with your observed gravity data. Okay, this is the end of the live demonstration, so I'm now going to go back to my presentation to talk about real-world data. Okay, so before we commercialize VALEM, we run an early adopter program to test the inversion with the industry, and OMV was one of the participants. So first of all, I'd like to thank OMV and its partners for letting us show these results today, and in particular Michael Bem at OMV. I should also say that today I'll only give you a test of this study, as Michael and Taranish will be presenting this work in detail at the SEG in New Orleans later this fall. So in this first slide, you can see the survey area on the left with the acquisition line here with a 500-meter spacing. So it was a full tensor gravity gradiometry survey, but only used only GZ has been used in this study. So GZ was calculated by integrating the GZZ component. So OMV had done a conventional 3D gravity inversion on this data set in the past, but were not entirely convinced by the results, so they decided to try VALEM. And it's worth pointing out here that OMV had this gravity data on the shelf. So for them it was a low-cost approach really to improve their seismic imaging of the base of salt. So Michael followed a very similar approach to what we did with the synthetic model I've just shown you, and VALEM was used here to run a first pass at the base of salt. So they started without any salt in the model. So he had first to create a reference model and produce a residual gravity anomaly that you can see here on the left. So the reference model itself wasn't a simple task. In addition to the salt screening, the seismic imaging below the salt was extremely challenging due to some high-density shallow and mist grass, as you can see on the section here. So without much knowledge, they adopted an OCAM's approach, building the reference model, and went for a model as simple as possible. So on the left, as I said, you can see the remaining gravity anomaly map once they've done that model, which is assumed to represent the salt body only. So the dashed line here is the 0 milligal contours inside which salt is likely to occur. So here, those negative anomalies. So you can see that there are still positive anomalies outside the salt, which might indicate maybe, well, our background model is not perfect, and we might have underestimated densities. However, good enough to start an inversion. So using these two, they run a series of inversion with only the top salt as initial constraint, and they recover the salt model that you can see here on the right through one section going through the salt. So you can see that relatively flat here base of salt. The salt is in yellow here at about 2.2 grams per cubic centimeters. So the gravity base of salt was then fed back into the velocity model for validation. And here is a comparison of depth migration along one test line between the velocity model based on seismic interpretation only at the top here, and the velocity model based on the integrated gravimetric, seismic and well data at the bottom here. So the solid black lines show the top and base salt respectively on both these figures. So as you can see, the outcome of the VALEM inversion were positive. The VALEM base of salt was deemed very plausible by the seismic team. It was a realistic thickness and topography. And importantly, it has improved the seismic image in the pre-salt. So yellow arrows here point towards area of improved lateral continuity. Okay, I'm coming to the end of the presentation. I hope I've convinced you that hybrid gravity inversion can improve seismic imaging in the subsalt. Using a hybrid inversion approach, which uses layered earth modeling to efficiently model layered structures, combined with a constrained voxel-based inversion, we were able to recover a sharp boundary defining the base of salt. So it's fast, it uses high-performance computing to perform the inversion, it's flexible, we can incorporate complex geometries and 3D density distribution, which are appropriate in a complex problem like subsalt. So it means that it's easier to go back and forth between the gravity and the seismic interpretation. So ultimately, it should reduce uncertainty and improve the model confidence. So in terms of future development, well, at present, VALEM is optimized for base of salt modeling using conventional gravity, GZ. However, as we continue our development, it could include inversion of gravity gradient for the base of salt and magnetic data for basin analysis and subsalt imaging. Well, thank you very much for your attention today, and I'm now handing back to Bruce.
Okay, thanks, Gode. I'd like to underscore a point that Gode made about OMV's participation in our early adopter program. Oil companies are looking to create value from all of their data. Sometimes it includes historical data. And the better able they are to integrate all their data sets together, the better off they are. And if they can do that at low cost, especially in this low price environment, all the better. Okay, so now we're going to take your questions. We have about 10 minutes. If you haven't already sent them to us, this would be a good time to do it. So as I said earlier, you can do that by entering your questions in the question box in the GoToWebinar control panel. So while you're doing that, I'd like to share two things with you, plus we have one more poll to take. First, we will be sending you a recording of today's seminar in about a week. It'll take about a week to prepare it. Secondly, if you're interested, VALEM is commercially available as a software service extension for GM-SYS 3D. So we have flexible pricing options, including short-term project subscriptions and annual subscriptions. For more information and to get started using VALEM, please take a few moments to respond and we will contact you.
Thank you, Bruce, and thank you, Gode, for your presentation. We have a few questions coming in through the questions pane. The first question is about gravity tensor components. And one of the participants is wondering if including other gravity tensor components would help, or if it is possible to perform a VALEM inversion with gravity gradiometer data. VALEM is currently optimized for GZ, or regular gravity observation data. As Gode mentioned in the presentation, future developments will include the support of gravity gradiometer data as well. We have another question asking about geosurface or multi-depth or multi-Z surfaces, and if these surfaces can be used to represent complex salt bodies in GM-SYS 3D. Multi-Z or triangulated surfaces or closed geosurfaces can be used to represent complex bodies in GM-SYS 3D. The first version of VALEM will only allow the inversion of a base of salt layer that is defined using a standard or traditional single depth grid. Future iterations of VALEM will include the ability to invert on closed surfaces or multi-Z bodies. We have another question here. Can VALEM be used for basalt bodies that may make seismic interpretation difficult? So the current iteration of VALEM is set up for gravity inversion. If your basalt basalt body has a suitable density contrast, then it can, in theory, work. And in future developments, we are also developing a magnetic inversion for VALEM for basalt as well. And the last question that's come in, can VALEM be used to invert for the top of salt? So VALEM is tuned to invert for a 3D density distribution beneath the layer of interest. So when you invert for the base of salt, the density distribution beneath the base of salt is defined using a three-dimensional voxel density distribution. If you're since the density beneath the top of salt is, I'll reword it, if the density beneath the top of salt is also defined using a voxel distribution, then again, in theory, this is possible to invert for. However, the density contrast within the salt body may not be sufficient for the inversion to work very well. This is something that we can discuss in more detail and perhaps set up a trial to test. And the last question, how do you account for the nil zone in salt modeling, or the nil zone is also known as the area where there is zero density contrast? So in the example that Gode has shown, the salt body actually crosses the nil zone and was well recovered, but this is partially because the top of where the salt has crossed the nil zone was defined by the top of salt grid, which was used as a constraint in the inversion. So in the case where, or in this particular case, the top of salt passed the nil zone, and since it was used as a firm constraint, it was held fixed during the inversion process. Okay, that appears to be the only questions about VALEM or GM-SYS 3D. Oh, we've got one more coming in. Nope. Sorry, that was just a comment to a previous question that I answered in the chat. We don't have any more new questions coming in, and we are approaching the end of the question and answer period, so I'll turn it back to Bruce. However, I'll encourage our people to email, or our participants to email their questions in even after the conclusion of this webinar. Thank you very much.
Okay. Thank you, Taronish. So as he said, if you have more questions, please feel free to contact us. We're always available. We would also love to hear how you use Geosoft to advance your projects. And if you'd be so kind, we'd appreciate you sending your stories to us at explore@geosoft.com. Anyway, it's time to wrap it up today. I want to thank you, and on behalf of Gode, Taronish, and the entire Geosoft team, I thank you for participating today and for joining us. That's all. Thank you very much. Bye.